I've known Noel since 1980 when he was a young lecturer at Flinders University and I was a young lecturer at the University of Newcastle upon Tyne. He left his native land for a very successful career in America but returned relatively recently to the University of Wollongong where we re-met and team taught a couple of years ago, which was great fun. I will just say he's eminently worthy of the Barnett Award for many reasons, some of which he will display now and some others I think he will tell us about this evening at the honours ceremony. So, Noel Cressie.
Thank you. Hello everyone. Am I mic'd? Yep, you can hear me. So it's really fitting that the Barnett Lecture, this is the second Barnett Lecture, Jonathan Torn gave the first one a couple of years ago. Really fitting it be here in Manchester. Vic Barnett actually got all his degrees here at the University of Manchester. And so I'm really happy to be in Manchester myself for the first time. In my talk, there will be some connections with some of the numerous things that Vic Barnett did in his career, one of which was environmental statistics. But he was also head of mathematics and statistics at the Rothamsted Experimental Station, and you will see that that theme does come up as well. All right, so find where we are. I'm not sure if we're on that part of the map, but this is our planet. It is a fairly lonely planet. People are looking for planets like ours. They're not all that close, but it would appear that there are more of them than we thought. But let's just say it's all we've got for the moment. And within that planet, we have the carbon cycle. The Earth basically comes with its carbon, and it's a closed system. We have all we've got, and whatever we're doing with carbon, we're moving from one pool to the other. And this is a very cartoon view. It comes from the IPCC report, Intergovernmental Panel on Climate Change report, of what the carbon cycle might look like. What's bothering us all, I think, is that a lot of carbon in the form of fossil fuel is in the ground, somewhat inert, and carbon hurts us a lot when it gets into the atmosphere for reasons I'll go into in a minute. Atmospheric carbon, in terms of carbon dioxide, is a greenhouse gas, and there are serious consequences of having too much of that greenhouse gas in our atmosphere. So this is a three-number summary. People play with these numbers a lot. There's this general feeling that if we keep climate change to 2 degrees Celsius, then we'll be able to manage our environment. So far, by the way, this 2 degrees change is from the Industrial Revolution. By now, we're up 0.8 degrees, and I'll make a case in a minute that might point to the fact that we're already well on our way to 1.2. It just hasn't manifested yet. Carbon dioxide is a long-living gas in the atmosphere. The second number of the three-number summary is the number of gigatons of carbon that it would take to get us to 2 degrees. It's about 565 gigatons, that's an estimate. And we'll get there by mid-century. The third number in the three-number summary is the reserves that companies like Exxon and BP have in the ground in terms of fossil fuel, and it is about 5 times as much as it will take. And there's a small message to this third number of the three-number summary. Do we think that those companies will leave their fossil fuels in the ground? If they did, their stockholders and their shares would plummet, would drop tenfold, 100-fold. So there's a lot of pressure, I guess, in making sure that this carbon comes out of the ground and goes into the atmosphere. And equally, we know that it's a very strong greenhouse gas. It's the most important greenhouse gas, and it will increase our temperatures. And by mid-century, we only need 565 gigatons of it before we'll reach the 2 degrees. There's really there's sort of a consensus, and when the accord was signed in Paris last December, this 2 degrees keeps coming up. We read about it. I read articles, and I even do analyses which show that in different places regionally we'll see more like 4 degrees Celsius. So it's somewhat of a fictitious number, and the feeling is that if we get to 2 degrees and maintain the 2 degrees, our existence will be pretty much the way it is now. Actually, not sure if that's true. We're already seeing the effects of climate change, and we're only at 0.8 degrees, but that's a small piece of anecdote on my part. So carbon is quite abundant. We were in equilibrium before the Industrial Revolution. We put out about as much carbon as was absorbed. Since then, we're out of balance. About 10 gigatons of anthropogenic carbon is put into the atmosphere per year. About half of that is absorbed into sinks, and the other half remains in the atmosphere. It is a long-lived gas, as I mentioned. 20% of the carbon that goes into the atmosphere this year will probably stay in the atmosphere on the order of thousands of years. So the point is that when we take a sauna and we turn on the sauna, we don't expect it to be immediately hot. We have to wait until it warms up. And then we turn off the sauna. We don't expect it to be immediately cold either. And so we're dealing with treaties of the sort to limit the amount of carbon in the atmosphere, anthropogenic carbon, and yet we have all of this carbon hanging over our heads, this long-lived feature of carbon dioxide in the atmosphere, and we're playing with this number of 2 degrees Celsius as a limit. We don't even know if it's a good limit, and secondly, we're probably already locked in already. I mean, if we stop carbon dioxide emissions of an egregious nature tomorrow, we're probably already locked in. There is a way to measure carbon dioxide in the atmosphere, and that's a mole fraction in terms of parts per million, and we just reached the 400 parts per million threshold this year. Carbon is very nicely mixed in the atmosphere, and so you can put a monitoring site on the top of Mauna Loa volcano in Hawaii and simply see the carbon that has come from many, many places around the Earth. And so that mixing, in a sense, it tells us there's a lot of stability in the measurement of carbon dioxide in the atmosphere. And it was simply clear that for the 400 parts per million was a global level that was reached in 2016. There was no argument because it mixes so well in the atmosphere. So you might wonder what a spatial statistician is doing looking at something that mixes really well and actually doesn't really have a lot of spatial signature, but it does in a way that I'll describe in a minute. Okay, so talk about a juggling act. I like the image. Our climate system has a lot of features to it. There are different clubs in the atmosphere. One is a carbon club, and it's spinning, and I've tried to make a small case now that the carbon club is actually getting a bit heavier, and it's spinning out of control, and to push the analogy, we might have already actually dropped the club. So there are attempts, of course, by we humans to try and measure what's going on, and there are a lot of monitoring sites. A lot of these sites are actually ground-based, but as you can imagine, being ground-based and you've got a global coverage to make up, can't really get good global signatures around the Earth. And I mentioned before that carbon dioxide in the atmosphere is well mixed, so why do we want to know what's happening, in different parts of the Earth? And the answer is because we really want to mitigate, and we want to try to stop carbon dioxide coming out of the Earth's surface, getting into the atmosphere, and when it does, we want to look for ways to get it back into the Earth. And so while we measure carbon on the top of Mauna Loa and we see it well mixed, and our real goal is to work out where the sources and sinks are, the flux of carbon out of the Earth's surface. And that is a highly spatial process. We know oceans take up a lot of carbon dioxide. They become acidic in the process and turn into carbonic acid, and it does affect the food web in the oceans generally. We know that fires are a big source of carbon dioxide in the atmosphere. We also know that burning fossil fuels are a big source, and in particular cement factories are hugely effective in putting carbon dioxide into the atmosphere. So we know some of these gross features that I showed you on the second slide from the IPCC report, but they're very gross and they don't get at where mitigation might occur at a national level or a regional level. And so the whole goal of studying carbon dioxide, atmospheric carbon dioxide, is to work out where it's coming from and where it might go to in a mitigation strategy. And that's where the spatial statistics comes in. All right, so if you can't measure it, you can't manage it. This represents a whole load of satellites that NASA very interested in measuring and managing the Earth system. And this satellite here, OCO2, is one that I'm particularly interested in. I'm on the science team of NASA's OCO2 instrument. I'm one of several statisticians on that science team. And it was launched in July 2014, so it's been flying for about 2 years. This is the launch. I was present at the launch. I did not see that because there was a lot of fog. And you'll see in a minute, basically we heard it, we kind of saw a flash of light, and then it was gone. This picture was taken a lot closer to the launch pad than we were allowed to get. But anyhow, I was there, and it was very exciting. It was about 2 a.m, and we all went back to the hotel and had a few drinks. So this is a picture, turned out it was astronomy picture of the day, of the launch of the satellite, and there's very low-lying cloud and fog here, and this is in July of 2014, and you can see the satellite has reached a very low orbit. MECO is main engine cutoff, and fairing separation is when the actual satellite itself, the instrument, is pushed out into a low orbit. After a couple of months, it gradually climbs to about 800 kilometres. The orbit's about 800 kilometres. And in the process, it does about 14 orbits a day, and it's designed to cross the equator about 1 p.m. local time. And in about 16 days, it does a repeat cycle. So there's a very strong space-time component to this. This is a picture that was done by artists at NASA of the satellite. It's like a big telephone booth, if you like Doctor Who, there it is. And it's, as I said, orbiting at about 800 kilometres above. And it's in a train called the A train or the afternoon train. And it's designed so that satellites in front of it are collecting data on aerosols. Aerosols are important in composition of the atmosphere and in measuring carbon dioxide, actually. So these clubs that I'm talking about are spinning, and they carry information and they carry uncertainty. Even the theory of how the atmosphere is working, the physical models are uncertain, and it's really important that statisticians sort of get in there and deal with the uncertainty in ways that perhaps a physicist would not, and that we try to do it in a somewhat coherent way. So I want to point out that throughout a lot of this work, and done by physicists and done by statisticians, done in conjunction, the two talking to each other, Bayes' rule, they're not particularly Bayesians, but they are interested in predictions and predictive distributions. And so Bayes' rule is actually the superhero of everything that's going on in this very large environmental statistical problem. And here it's sort of Earth-based, Earth-observing-based, but any of you who've worked in astronomy knows that the astronomy profession, sort of looking into outer space, have discovered Bayes' rule some time ago and use it consistently and often. Anyhow, so Bayes' rule is about taking the data that you have, thinking about the process that you would like to look at or like to make inference on, and working out what the predictive distribution is of that process given the data that you have. And that's what's going to drive this talk, actually. Okay, so OCO2 instrument is actually, it's a do-over. The reason why it's got a 2 there is because OCO, with nothing in front of it, actually the launch, I was at that one too, sort of 5 years earlier, was brilliant, great launch, but that fairing separation that I mentioned, you know, the main engine cut off, the fairing separation didn't work with OCO, and the instrument ended up crashing into the Antarctic, or the sea off the Antarctic. And so there was never any, it was a lot of money, $300 million or something at that time, went into OCO, and NASA, through a presidential initiative from President Obama at the time, decided to have a do-over. It's very rare in remote sensing missions and campaigns that you get a chance to have a do-over. But in this case, carbon dioxide was seen as extremely important and so absolutely essential. And so another $400 million, and this time it has actually been in orbit and collecting data for the last 2 years. So I mentioned a little bit about the features. The last dot point there about a physical forward model has to do with this notion of uncertainty in the physics and uncertainty in the measurement that Bayes' rule is really important in giving us. So this represents a repeat cycle, 16 days. On any one day, you'll see a ribbon going around, and these ribbons eventually join up, and you'll see a full repeat cycle. You'll notice there's not a lot of measurements sort of around the poles. There's a reason for that. The signal-to-noise ratio is not so good in that area. Certainly at certain times of the year it's terrible. And any one of those points, and those points, by the way, are emphasised for graphical purposes. There are probably about 5 million points here. But any one of those points requires a retrieval. And I'm going to take you through very quickly through what it takes to get one retrieval. And it has to be done in about 2 minutes, because there's a lot more coming where that came from. So there is a timing issue, a computational timing issue as well. This is a data vector. It's actually in 3 parts, and I've coloured it that way. This is a data vector for one retrieval, one of those little points, one of those 5 million points. The data vector is about 3,000 dimensional, and it represents the state of the atmosphere. And this is called remote sensing, right? So, in fact, what's happening is light is being reflected from the surface of the Earth, and it goes up to the satellite 800 kilometres high, and a very sensitive camera takes a picture. It's in the infrared part of the spectrum. It's not in the visible part. And there are different parts of that spectrum that are sensitive to carbon dioxide and to oxygen. And the combination of carbon dioxide to oxygen allows one to construct a model for the way these radiances, these energies, are related to the state of the atmosphere. And that model is given here. And the data here are about 3,000 dimensional, as I mentioned, and they have radiances in the carbon dioxide sensitive parts of the spectrum, as well as the oxygen sensitive parts. And the atmosphere I've written as a vector Y. That vector is anywhere between 50 to 100 dimensions. As I worked on this problem, it was at 112 dimensions, and then people found different ways to summarize the atmosphere. It's now down to about 46 dimensions. But there are 20 of those dimensions that are really important, and they represent carbon dioxide readings at 20 different pressure levels in the atmosphere, from the surface to the satellite. And so here's where Bayes' rule comes in, because the physicists have a feeling as to what the atmosphere might be distributed like. Usually these distributions are Gaussian, but there's a prior mean, what they call a prior mean and a prior covariance, what I would call a process mean and a process covariance, or what you might call, if you do state space estimation, these would be the mean of the state and the variance of the state. Interestingly, there are parameters, and this is where, if you were really full Bayesian, you would want to put priors on them, or you might want to be an empirical Bayesian and estimate them from the data. This does not happen with NASA, as much as I've sort of suggested it. A large reason why theta is simply fixed and got from table lookups is because computation has to be done in 2 minutes. And so to take the extra effort to make inference on theta is not thought to be worthwhile. But that represents something that I think we could all get involved in. So what the rocket scientists want is some measure of carbon dioxide where they have a certain amount of certainty or uncertainty, a small uncertainty. And the way they get that is they take these 20 pressure levels and they average them through the column. And that gives you something called XCO2, which is the column averaged carbon dioxide. So imagine this, that because there's so much uncertainty in the original 3,000 dimensional radiances, and it's very hard for a satellite looking down at a projection on a column to back out what the carbon dioxide would be at 20 pressure levels. If you think about it, it would be much easier if we got values and measurements of the column itself, the whole column, and then use that as our measure of carbon dioxide in the atmosphere. And that particular map I showed you is precisely XCO2. You see that over here? So that XCO2 is the column average carbon dioxide value. So some compromises are being made here because you're really interested in carbon dioxide near the Earth's surface. And yet now this is the state of the art. Now there's averaging of the carbon dioxide through the column so that you get better variance. And there will be an attempt right at the end of the talk to back that out and work out what's happening at the Earth's surface. So I want to step through fairly quickly here. So just to this single retrieval, if that model were linear, we would have it in one step. And provided these inverses are all okay, we'd be able to calculate our best estimate of what's happening in the atmosphere, y hat. F is not linear by any means, and so what people do is they implement a Levenberg-Marquardt algorithm with a certain amount of additional, you might say, this gamma inflation parameter stops things going to hell sometimes, and it allows better convergence properties. The state of the art in OCO2 in choosing this gamma is sort of like, I don't know, it's written down somewhere, but let's just say it's almost not reproducible, I could say that. There are, if you like, a lot of engineering solutions that go into choosing gamma and these various quantities. So I've had some influence in, I think, improving that, but only small, in determining where these evaluations of the Jacobians are and various things. So I've spent some time trying to learn what the engineers are doing, and I've tried to help to improve it. So back to this set of data. Now I've given you what it takes to get one of those dots. Now we have maybe 5 million of them. I just want to make one point here. I'm going to collect all the data and I'm going to call it Z sub D. And that would be the estimate of the column averaged carbon dioxide, because there is a difference between the true average, right, and then the estimate. And that is actually mixed up a bit in the literature, in the remote sensing literature. And so I've tried to be careful in thinking about the X hat itself, which remember is G of Y hat, and Y hat comes out of the Levenberg-Marquardt algorithm, that the data would now be collected. For example, in a period of 16 days, I would have 5 million of these, okay? Or in a period of 4 days, I'd have a quarter of that. And on occasions, one plays with the space and the time in order to get sort of more replication, you increase the time, but in the process, of course, you don't get total comparability. So I now want to move on to back to the past, and this is obviously Sir Ronald Fisher, and there's a little bit about his life there, but what I want to get to is these notions of design of experiments, because you might think that what we have with the OCO2 instrument is an observational study, and you're partly right. But I want to see what it is and share with you what I think are some of the common features of agricultural experimental design and what we see with the OCO2 instrument. So we'll take a little break and we'll go back 100 years or so and look at, mainly at this notion of randomization. I'd like to sort of look at this idea of yields, because I'm going to make a connection between agricultural experiments and what NASA's doing with the Orbiting Carbon Observatory in about 10 or 15 minutes. But I want to walk through this a little bit because, randomization was chosen to try and deal with this unfortunate problem of perhaps a treatment being put with a plot that was either more fertile or less fertile than it should have been, and come to the conclusion certain treatment was the better treatment, but only because of the way the treatment was applied to plots. So what Fisher did was to invoke some randomization. And what I would like to sort of point out today is that there is another way to look at these plot effects. And those plot effects could be seen as random effects that have spatial dependence. And I'll try and just sort of walk your way through that. All right, so let's sort of look at a very cartoon view of what the problem is. I'm thinking about a completely randomized block design. I just want to take one block for the moment. Everything could then be indexed with a particular block of interest, but let me just look at one particular block, and I have the same number of plots as I have treatments. And so I'm now interested in assigning the treatments to the plots. And if I have a fertility gradient that looks like this, and I assign the plots and the treatments A, B, C, D, E, then even if A is the worst treatment, I might end up with declaring it to be the best, that it's superior. And in a completely randomized block design, you have a lot of replication, of course, where you get the chance to randomize a lot. But here in just the first block, I could do a randomization and then another one and then another one, and I'd end up making inferences based on the randomization distribution. I'd like to try and write that model down. Certainly, I've already written it down here as the treatment effect plus the plot effect. There's an assumption in there that there is no interaction. And what Fisher did by randomizing was essentially make that assumption right. And we'll see that in a minute. But I would like to make a point here that Yij, which is the true yield, it's not what we observe. If there are T treatments and T plots in that one block, in principle there are T squared, T times T values of Yij. And what we get is a look at only T of these, because I, the particular plot, has got the jth treatment on it. And so there's some selection. Now it turns out this assignment will be random in the case of what Fisher proposed. But so the point is that the data here, there are only T data. And obviously when I have B blocks, I have replication at that point, and so that allows me to do inference. But our goal is to infer these treatment effects from these observations. This Yij is something cerebral, you might say, and I look upon it as a hierarchical model, and I'll bring that out in a minute. Okay. So what Fisher did was to reach for the likelihood. Why, heck, he invented the likelihood, so why wouldn't he? But from this other viewpoint, that likelihood is actually can be written as an integral of components of variance of z given y, and y given theta, dy. And theta essentially consists of the treatment effects. It has other things in it too, like variances and things like that. So my point here is that there are actually two yields. One is the true yield, and the other one is the observed yield. And I think a lot of the work that Fisher was doing, and at Rothamsted, people were looking at the observed yield, and you can't blame them. But I think a more modern view of that particular approach would be to think about the true yields, the yij, and they're actually t squared of those, because we can think of a counterfactual where a particular treatment went to a certain plot. I mean, it didn't. It had to be assigned in some way or other, but we could think about the counterfactual. And I think there's a lot of benefit in doing that, as I'll point out in a minute. So the question is, where did that y go? And I think it was never considered. But I want to pull it out and see what it could be. And what I want to do with it is I want to make the plot effect equal to some constant plus some sort of random effect, which I'm going to model as a spatial random effect. You might say, well, that guy's a spatial statistician. Of course he'll do that. But I want to quote something from Fisher in 1935, and I believe this was what sort of motivated Fisher to introduce randomization. I quote, "After choosing the area, we usually have no guidance beyond the widely verifiable fact that patches in close proximity are commonly more alike than those which are far apart." I think Fisher was probably one of the early spatial statisticians, but he didn't want to get into the modeling of the spatial statistics. He wanted to randomize to deal with it. So what I want to do is, in a sense, go back to the past and see what would happen if I made this delta here, this one dimension, down a block. Obviously, when I have lots of blocks, I might have a two-dimensional, or I might have a lot of one-dimensional spatial models. But I want to put on this, let's say, an exponential model. This is just an autoregressive process down the block. And the choice of this exponential is not particularly important. It could be something else. And in general, what I've done in my work and what others have done too is that if you do inference on the alphas and you incorporate the spatial dependence, you get more efficiency. But let me just sort of go into that in a little more detail. So let's see what the effect of that is once you randomize. And I'm going to choose a notation that basically puts a z star j on the quantity which comes out of that, if you like, is the z associated with treatment j. But I'm going to pull out this hidden process and consider measurement error. And at that point, I've now disentangled the true process, the true yields, from the measured yields. And I'm going to write z star j as y star j plus epsilon. So I can go in and I can actually calculate all these moments of y star j, the true hidden process. And I have randomization to deal with. And when I make that calculation, I end up with the covariance between y star j and y star j prime, treatment j and treatment j prime, the data associated with, equal to something that doesn't depend on j and j prime. So that's something I think that we all knew, that there was this constant intraclass correlation associated with randomization. But all I've done is put in a very simple spatial model. This time it has a spatial random effect. I put on the spatial model and I've incorporated the measurement error. I rewrite my spatial effect. I combine it with the measurement error and I call it EJ. And I admit I'm playing with symbols here, but I'm trying to motivate how one can deal with this hidden process Y and what benefit it can give us. And I hope you'll see in a minute we get quite a lot of benefit out of it. So the underlying variance of the Zs has this constant intraclass correlation. And some of you and many of you may know that this type of dependence was something that was of great interest to Fisher, to people who came after Fisher, Kempthorne, people who came after Kempthorne, Ziskin. Ziskin was Kempthorne's student at Iowa State. And there's a very long and excellent paper by George Ziskin talking about what forms of the variance of E would give us the ordinary least squares estimate as being the best linear unbiased estimate. This is this long paper about how we can get the best estimate out of these sorts of variance-covariance structures. And what I've done is I've put on a spatial dependence model, I've introduced randomization, I've produced that covariance structure, and I'm now back in Ziskin's world and Kempthorne's world, and before that, Fisher's world, where we can estimate alpha using ordinary least squares and know that it's optimal. Okay, so let me just now back up a little. What would Fisher really like to do? I think he thought that conditioning on ancillaries was good. I know there are a number of people in this audience who believe that conditioning on ancillaries are the right thing to do. And in fact, the randomization, this vector I, which tells you which treatment was assigned to which plot, that randomization is an ancillary statistic. So now we've got our data, we've actually randomized, now we can do an analysis conditional on the ancillary. And if you do that analysis conditional on the ancillary, then the spatial dependence reappears. It's perhaps not surprising, but what I'm doing is sort of going back and applying principles to randomized data coming from a randomization experiment, and then doing what we believe we should do, and that is conditional ancillary, and we get back to spatial dependence. And I think this is an explanation for why when you do a spatial analysis of randomized data, you're able to get efficiencies that are considerably more than a non-spatial analysis. And in a paper in Technometrics, a student of mine and I demonstrated that. Okay. So you could, and I like to think about it this way, is that these Ys, these hidden processes, are coming from, in a sense, a field. And the randomization has actually chosen only parts of that field. And the circles represent things that could have been chosen that weren't. And that's the counterfactuals that I was referring to before. And I'd like to now push the idea on, because I like predictive inference, and I like to think about Bayes' rule, is that the data are actually the yields and the randomization, both. And I should actually condition on both of them. And so when I condition on both of them, some very nice things start to show up. I get Gaussian measurement error, and I get a Gaussian spatial process for the underlying Y process. And I can incorporate, I'll just sort of quickly go to the next slide, I can incorporate alpha, the treatment effect, because it's within Y in general. And I can start to think about inference on alpha, not only on alpha, but on the underlying hidden process Y, given the data and given the randomization. And that's what predictive inference, that's again a principle that says I condition on the data, and I think about the things that I don't know, the unknowns. The unknowns are here are the treatment effect and the underlying spatial random effects that I've modeled. And I can then look for the posterior distribution of Y, given that. If I want to be a fully Bayesian, of course I put a prior on it, but as an empirical Bayesian, I could simply take that distribution and plug in perhaps alpha hat ordinary least squares. Okay. So now let's get back to rocket science. So how is this relevant to OCO2? And the answer is there is relevance. And can we do randomization? And the answer is maybe, and I'll share that with you now. Okay. So the blocks here would be things like land-ocean. It's well known that these retrievals are different over land and over ocean. have latitudinal gradients. Another block that I haven't put on would be seasonal. Carbon dioxide has a very seasonal component in the northern hemisphere versus the southern hemisphere. There's a strong reason for that, and the reason is because obviously the uptake of carbon dioxide, a lot of that is through photosynthesis, and the seasons are different in different parts of the hemisphere. So there's a lot of seasonality. What about treatments? Turns out, and we're not sure why, is that when the instrument is actually looking straight down, we get a different measurement than if it's pointed at what we call a glint spot. The idea is to maximize the signal-to-noise ratio, and so the instrument is able to point at a reflection of the sun, which maximizes the signal-to-noise ratio. If you're looking straight down, the sun is oblique often, and so you don't get the signal-to-noise ratio that you want. So it's possible, and they do, point this instrument differently on different orbits. So there are Plot's effects, yes. I've made a strong point here, that spatial dependence, and actually Fisher makes the point better than me, is that Plot effects and spatial dependence are very much the same thing. And is there replication? Well, in a certain sense, yes. 5 million, I would consider, per every 16 days would be a strong argument for replication. The only issue is, am I replicating the same Earth, if you like? And the answer is no. Obviously, we play that game all the time, don't we? Where don't have exact replication, but we come close if we look for little windows of time and windows in space where things should be very much the same. And they do play that game a lot in the OCO2 science team. Is there an experimental design? Well, not really, but there are opportunities to actually, on the next orbit, to point the instrument, to change the treatment. And it's well known that certain orbits are over land and certain orbits are over ocean. So there is an opportunity to think about a factorial design that takes land-ocean latitude as factors and treatments, which would be NADA and glint, and work that into a factorial design. The engineers don't like thinking about this because every time the instrument points at a different part of the Earth, they use little traction wheels. And there's, every time you use it, there's a little bit of friction, decreases the lifetime of the satellite and of the instrument, takes a little fuel, extra fuel to do that, which again decreases the lifetime of the instrument. So let's just say there's some opposition to trying to be fancy about doing an experimental design, but I think a strong case can be made. In particular, so the physicists have no problem dealing with spatial dependence, and so there's no argument to be made there. I think the argument made is to get these treatment effects sorted out, and that's something that I think we know how to do quite well. Can we make inference on the underlying spatial process? And the answer is yes, we can. That's something that we do know how to do, at least I think I do. This slide I'm not going to leave up for very long. It just tells you the particular form of kriging that I used. As you can imagine, if you've got 5 million data points, or if you've got a 4-day block and you've got 1 million data points, you're going to have to do something to deal with the big data issue, and we do. We use something called fixed-rank kriging. This particular slide is an apology slide, and there was going to be a talk based around this slide, and that was the abstract which was sent in 3 months ago. I got excited about going back to the past and looking at Fisher and having Rothamsted sorted out and introducing ideas in orbiting carbon observatory. So I made a decision just to put that slide up and tell you that we're taking these ideas of one instrument and moving them into several instruments. Remember that early slide I showed you of NASA's configuration, its fleet of satellites? Every one of those instruments takes a part of the atmosphere and a part of the atmosphere that we might be able to use in our retrievals of orbiting carbon observatory. Now, I'll give you an example. Aerosols. Aerosols are the biggest problem we have, because if you're looking at the reflection of the sun from the Earth's surface and you're looking at the path length and the energies absorbed during that path length, if that particular reflection happens off a lot of aerosol particles, the path length is not a straight line anymore, and so those calculations become very complicated. And to work out how many carbon dioxide particles there are in that column becomes very complicated, because they're coming from different parts of the atmosphere due to reflection on aerosols. So in the A train, there is an aerosol instrument called Calypso. And so what I'm getting at is that we are very interested in our work, and it's joint with Hai Nguyen and Amy Braverman, is to do something we call data fusion. And we have spatial statistical data fusion, spatio-temporal data fusion, and multivariate spatial data fusion. These are papers that either appeared or in process. Okay, there's my apology slide. Let me get back to doing this kriging and this mapping. And I have believed for some time that the Earth is not flat. I've believed for some time that it is spherical. I certainly in my travels I prove that. But I think we should, when we're looking at a per unit area quantity or a per unit volume quantity, we should use equal area projections, if at all possible. And there's this really cool method called the icosahedral Snyder equal area prediction, which has been around now about 20 years, that finally NASA is feeling that, you know, the lat long grid, while they like it, everybody uses it for navigation, when it comes to geophysical interpretation, we might go to an equal area grid. So what one does is put down icosahedron, a spherical icosahedron on the Earth's surface and then flatten it. When it's flat like that and you end up putting hexagons on the flattened icosahedron and then rewrapping them on the Earth's surface, you get equal area projections, except for that pentagon there, which makes it all fit together. There are only 12 pentagons, and as we go down in resolution, there are still only 12 pentagons. Okay? And what you do is you do your mapping, you do your kriging, you do your neighborhood structure on the flattened icosahedron. You'll notice that there's some filling in needed in order to look for neighborhood structure. And then you wrap it back on the sphere when you want to do any particular graphics. So what we did is we did that. We have a colleague of mine, Andrew Zamit Manjon, has written a package called FRK, means fixed rank kriging. And you have the option to do this on lat longs or on hexagons, and so we've done this on hexagons. And this represents our map of XCO2 on the 1st of the month and the 15th of the month for about 5 months. We can do it on every day in the month, but I just don't want to bore you with this. So by the way, the bottom plot represents the standard errors associated, the kriging standard errors associated with it. The top plot, I'll just go back to the beginning. The top plot represents the spatial dependence of XCO2. And as I said before, you know, this mixes very well in the atmosphere, so why should we care? And the answer is we care because if we get a really good idea of XCO2, we can do flux inversion and work out where those carbon dioxide molecules are coming from the Earth's surface. Oh, what happened? Well, the instrument turned itself off for a day. And we got a prediction because we used data from the day before and data from the day afterwards. But as you can imagine, the standard errors are huge. But we do get standard errors, and we do get predictions. This is interesting, and it shows that we get low standard errors over land. I think that's right. Yeah. And higher standard errors over the ocean. So this is an indication of this effect that I mentioned, these factors of land, ocean, and treatment of nadir and glint. Okay, so this is my slide on surface fluxes. It's maybe I've got one more. It's not a lot, but it'll just give you some idea of where the science team is going. They're chasing surface fluxes, and these nuisance treatment effects of land and ocean and nadir and glint are causing some trouble, because when some things go in, fluxes change, as you can imagine. And if they put in all the land glint data, then they get a different answer than they put in data from surface fluxes. And our job as statisticians is to try and sort that out and to get rid of these nuisance treatment effects. One component that's being debated enormously is this covariance matrix of ZD. Remember, this is a 5 million dimensional vector, and this covariance matrix, well, let's just say there's some disagreement as to what it looks like. The current state of the art is to make it diagonal, as you can imagine, engineers, physicists, we've got this big matrix, we don't know how to take its inverse, so we're going to make it diagonal. I'm pushing back on that because I think this fixed rank Kriging model could deal with it. The other thing that's happening is the components that go into it along the diagonal, which I've called S1 hat up to Sn hat, they are too small by a factor of 1/2. And there are strong reasons for that, and it usually is coming from the aerosols that I talked about. But this is an ongoing process, is to get those, even if you're going to make this a diagonal, you better get the diagonals right. And the reason why you better get this right is because there is another Bayes rule, which is using transport of carbon dioxide molecules to get back at what's happening at the surface of the Earth, the fluxes. Now, that's a whole other talk, and it's actually a whole other exercise, so I don't want to spend too much time on that. I've really brought you to the point, to the science point, is what we want is highly precise carbon dioxide fluxes at the Earth's surface, because we then know what we can do to mitigate this incessant increase of greenhouse gases. Okay. So here we are back to the future. I believe greenhouse gases are a primary cause of climate change. By the end of the century, it's not clear whether we'll have life as we know it, sustainability of the Earth's ecosystems. We'll need mitigation, and when we need mitigation, we'll need strong spatial maps of where we could mitigate. And this last slide on flux inversion, it's very hard, because you can imagine it's a huge inverse problem. A lot of people are working on it. We're working on it at the University of Wollongong. We have a group working on it. But I believe our future depends on it, and so I hope I'll be back sometime to talk about that part of my work. Thank you very much.